All right, this is DES, okay? Used for quite a while. Secret and public key encryptions, okay? So symmetric, remember there's one key for encryption and decryption. If we lose the key, we're kind of out to lunch. They got it, okay? Same key is used to encrypt and decrypt. I thought I turned off the advance on this one, oh well. One key per channel, and then you all know how to calculate the numbers. You're going to see that again on another test. Take guarantee on both tests, but you're going to see that again. We've seen it on like 4 or 5 lectures already, so you can see it again. Okay. Now, asymmetric, separate key for encryption and decryption. Nothing new here. One key to encrypt, one key to decrypt, or vice versa. 2 keys per user. All right. So symmetric algorithms, DES is one of those. Okay. The data encryption standard. Okay. We also have skipjack, which we will not be covering in this class. Okay. We have AES, which we will be covering. Okay. Single key per channel, because it's the same key used for both. Okay. It's secret as long, it's only known by A and B, but again, if we lose the key, if either one will lose the key, you're kind of out to lunch there. Okay. Now what they're talking about, you can encrypt either way and decrypt either way. So it's the same key. Okay. All right. Some problems with it. Revealed keys. If I was to, I'm working with Cameron over here, and I reveal my key, what's that happen? What happens to Cameron's key? Yeah, everybody knows it's the same darn key, so it's not great. Distribution's also an issue. What if I have to get this key to him? He's in Russia or something. Okay. Large number of keys. So if I want to communicate with each one of you securely, I would need a separate key for each one of you. Whereas if I use an asymmetric system like PGP, I just need one set of keys. Yeah, I need your key as well to talk to each of you, but I would only have to worry about one key. Okay. All right, encryption was needed. It says a decree went through the land to find a good secure algorithm. We need a good cipher. IBM did it. They said, we will help you. Okay. It says one worthy competitor named Lucifer came forward. Yay. Okay, and it came up with DES. Okay, it's based on the Feistel structure. Okay, it's a symmetric structure where encryption and decryption operations are nearly identical, just manipulating the key schedule. So it's used the same way. Okay, it's considered a Feistel structure. This is based on the Lucifer cipher. Okay, and why was it named Lucifer cipher? Was it based on the devil? No. It was actually based on the demon algorithm. But not demon as in devil, demon as in short for demonstration. They were limited on the length of the name, so they originally called it demonstration, but that was too long, so they used the first characters of demonstration. But demon, people think it's the devil, so then they named it Lucifer. So really it was just, they demonstrated it, and that's the one they accepted. So it's kind of, it's weird, that's where it came from. Okay? All right. If you read the, what's the Stephen Levy book I told you all to get? Not Hackers. Crypto. Tells you all about it. It's really, really interesting. Couldn't think of the name there for a second. Okay, so it was short for the demonstration algorithm. Nothing to do with the devil. It was because the algorithm went in an APL, and it couldn't handle the length. Okay, so that you used demon. All right. 1977 was developed for use by the general public. Okay, this is a long time ago. I don't know about you, but in 1977 I wasn't doing much encryption. Accepted as a standard back then, both hardware and software. Which one's faster? Hardware or software? Hardware. Hardware's always faster, always. Okay. The algorithm, the complex combination of substitution and transposition ciphers, okay, 64-bit plaintext block, 56-bit key. They say the algorithm originally had a 128-bit block, but they lowered it because the NSA would be too secure. Again, that's all speculation. But either way, it ended up being a 64-bit block. Remember, 64-bit was still pretty big, and combined with a 56-bit key was still quite a bit. Okay. It's a 16-round algorithm, and the same algorithm is used for both. Okay. All right. Here is the schematic. Okay. It's kind of confusing, isn't it? I have a better one. Okay. way it works, you have initial permutation. See, this is the picture you see most places. I just don't like it. It's kind of hard to understand, isn't it? But I'll show you another one in a second. But that's the main one they show you. Okay, we have an initial permutation where we mix the text up. Okay, then we run through 16 cycles with key transposition. In other words, the key is changing while we're doing this. Okay, then we undo what we did. Okay, each cycle now, okay, with each of the 16 cycles, we split the left and the right half. So we take our text, so it's 64-bit. We take that 64-bit, break it into two 32-bit chunks. The first 32 bits is the left half, the second 32 bits is the right half. Okay? So we split it into two halves. The right side, we expand it from 32 to 48. Okay? So we go through an expansion permutation. Then we export it, or XOR it, I'm sorry, not export it, XOR it with the key. The key is actually 56 bits, but 8 bits is used for parity, which is error checking. So really, the key is ended up only being 48 bits, which we'll see as well. So it's XOR with a key. It goes through a substitution box, which we'll see. Then it goes, through and the substitution box brings it back down to 32. Then we go through the permutation, the right side only. Then we XOR it with the original left half. Okay. Then we put them all together again. So I'm going to show you a picture of what this looks like. Okay. Here's a picture of it. So on the left side, starting here at the top, we have our input. Okay. 64 bits. We have our initial permutation where we kind of mix it up. Then we split it. The left side gets the first 32 bits. The right side gets the second 32 bits. Okay. Left side, we don't do anything with it. Just stays the same. The right side, a copy of the right side is brought down to become the next left side. Y'all see that? So a copy of the right side at this point becomes the next left side. The right side then goes through the substitution box. We inject the key, which we'll see in a second. Okay. Then it goes through the permutation box, because actually it gets expanded upon here. Then it gets XORed. This plus sign is XORing with the original left side. Then that value becomes the next right side. So the next left side is actually the previous right side. Y'all see that? Then we do it 16 times. Cycle 16, we do the same thing, except we undo that initial permutation.
So the left side becomes this right side.
Right, the left side right here actually gets XORed in with the previous right side. So the next left side is actually the previous right side. Okay, so even here, the next, the right side becomes the next left side. Okay. So we do initial permutation, then we output the results. Okay. So far so good? Now we're going to look at each part. Okay. Here's the initial permutation. Okay. Kind of looks like you all remember spiral graph? Karen, I'm assuming you never heard of spiral graph.
I think I have.
Did you have one?
I don't remember.
That means no.
I have heard of it.
So you have heard of them.
That looks familiar. All right.
Okay. But it looks like spiral graph. Okay. You have an assignment to do based on this. Okay. The way this reads, okay. Okay. So bit 1 goes to position 40. Bit 2 goes to position 8. Bit 3 goes to position 48. Bit 4 goes to position 16, and so on and so forth. Read the assignment, because I might have the table mixed up on the assignment, but do the assignment based on the table I give you in the assignment, which we'll look at the end here. Okay. But what we're really doing is just moving them around, just like that picture right there. We're literally just changing positions. That's all we're doing. 32 bits, 64 bits go in, 64 bits come out. Just moved around. Okay?
So that table, does that ever change?
No, it's hard-coded. That's one of the reasons. This is hard-coded. The S boxes are hard-coded. And that's one of the issues. Why? Why is it hard-coded and no one will say? I'm assuming when they originally developed this, they had a reason for it. But it's not a good plan. It's just not a good plan. Okay. So the final permutation, if you notice, it's the initial upside down. Remember the picture 2 slides ago? It's the same picture, just upside down. All right. And there's what that does. It just really undoes what the other one did. Okay. All right, here's the cycle. So with the left side, we don't do anything with it. Okay, nothing with the left side. It brought down here to the bottom. The right side, we copy it, and we bring it down to become the next left side. The right side is ran through the expansion permutation, brought up to 48 bits. Then it's brought down. The key, two 26-bit keys are shifted. We'll look at the shift thing in a second. So we got a 56-bit key. Is brought through the permuted choice algorithm to bring it down to 48 bits. The reason we do that is to XOR, we need both of them to be 48 bits. So you're bringing the 48 bits of the right side that's been expanded upon, along with the 48 bits of the key that's been shrunk, XOR them together. Run them to the substitution box where we drop off from 48 down to 32. Then run it through another permutation box, and then that becomes, XORed with the left side. That becomes the next right side. Do that 16 times. Let's look at each one of those things. Okay. Here's the expansion permutation. You'll see that some items, like number 1, goes to number 2 and number 48. So some of them go to 2 places. Number 2 goes to number 3. Number 3 goes to number 4. Number 4 goes to number 5 and number whatever the heck that is over there. 7, I think. Okay. It's a little bit easier to see here. So bit 1, you need to do this on your assignment as well. So whatever's in bit position 1 gets moved to position 2 and position 48. Bit 2 goes to 3, 3 goes to 4, 4 goes to 5 and 7, and so on and so forth. Okay. I wrote a Java program to grade your homework, so I know it's correct. So each of you get to do a different word. Isn't that nice? Initially, you all did the same word, but then it was very easy to cheat. Now you each have a different word to do. All right, so that's expansion permutation. We took the 32 bits, we made it into 48. Here's the S boxes. Remember the S boxes? They were right here. That's the substitution box right here. Okay, that substitution box where we took 48 down to 32. Okay, so bits 1 through 6 come in, bits 1 through 4 come out. Okay, 7 through 12 come in, 5 through 8 come out. We're basically chopping off some, and you'll see which ones that happens to. All right, and there they are. So they tell you exactly which one goes where. You do not need to memorize that. I will not require you to do this part yet. Soon. Maybe next semester. But for those of you who successfully complete, you're good. You don't have to worry about it. Yeah, I just haven't made the assignment for you yet. Okay, there's the permutation choice box. Okay, it just basically mixes it up again. And they tell you which one goes where. But you notice all these are hard-coded. All this stuff is hard-coded, and that's one of the flaws in it. They're like, why is it hard-coded? That's stupid. Okay. All right, so we've seen the S box. We've seen the permuted choice box. Here's the key. Okay. Cycle 1, they shift the key bits by 1. Cycle 2, they shift it by 1. Cycle 3, they shift it by 2. And so on and so forth until cycle 16, they shift it by 1. Imagine turning the key, it's in binary, just shift it over by 1. And whenever try to make a really good password, just take an easy word on the keyboard and move your hands over by 1. Or you're typing something, you don't realize your hands are over by 1, you get gobbledygook on the screen. So shifting things by 1 really does make a difference. Okay. So that's what happens to the key. Okay. All right, the choice permutation, which is at the bottom. Now we're taking the 48 back down to 32. You'll see, like bit 9 gets dropped off. Bit 18 and 22 and 25, they just disappear. Okay, good. Why is that? I don't know. It's all hard-coded. They didn't tell me. This is just how it works. I'm assuming somewhere someone has written down why they did this, but they never really explained why they did it. It just did it. You know, it's there's a movie out there called The Beautiful Mind. Anyone ever seen that movie? Excellent movie, where he learns that the guy who's creating all these statistical theories just picked a number. It's like, we're going to start with 7. Why? I don't know, I just picked it. You can't do that. It's just, Yeah, it's really, if you haven't seen it yet, it's called The Beautiful Mind. Is that Russell? It's not Russell Crowe, is it? It is Russell Crowe? Okay. Really, really good movie. But, so yeah. So you can see, initially this was a secret algorithm. No one knew about it. So now it's kind of out in the open, and they're like, why did you do that? It was stupid. So, all right. So we know the cycle. We talked about each one of those. Okay? The algorithm itself, you do not need to know this. But basically, the left is the prior right. That's how you read this. And so on and so forth. The right becomes the prior left, because remember, the left comes down, get XORed with the right that came through the function, with the keys and all that. That becomes the next right. So, you don't need to know this.
So XOR is like whenever it takes like the ones and the zero, and then it takes, they just put them side by side, and then it takes it when they're one or the other, but not both.
Yes,
Okay.
that's I'm going to write this down here real quick. Format, font, we're going to come up with a big one. Well, I'll go 24. Okay. So if I have 0, 0, 1, 0, 1, 0, 1, 0, okay, then I have, okay, with XOR, it's one or the other, but not both. So we get a 1,
0,
0, whoops, 0,
0,
0, 0, 0,
1,
1,
1,
1, 0. That's XOR. One or the other, but not both. Everybody see that? You need to know how to do that because it's going to be on a couple of these projects here. Actually, not on this one. It'll be on your AS one. Okay. So the good question, I'm glad you brought that up. All right. So it's not critical you know, but that's basically what we talked about. Same hardware can be used for both. The keys are just submitted in the reverse order. All right, there's some problems with it. Okay, secrecy. Why did they do this? We don't know. Okay, details are still secret. There might have been, obviously there was a reason. I really doubt they put the numbers in a hat and picked them out. But why? We don't know. It's still secret. Okay, design flaws. They released information about the S-box. It says no S-box is a linear function with input. Has diffusion, change one S-box changes at least 2 outputs, which is good. Okay. They were chosen to minimize the difference between the number of ones and zeros when any single input bit is held constant. So what they're saying is, if bit 5 is always a 1, okay, they want to make it so the S-box puts out a different value in that position. But since they're hard-coding something to make that change, it causes other issues, okay? So it's kind of like you force someone to do something where they probably would have been better off on their own. That's kind of what they're talking about. Number of iterations, did we really need 16 times? They've proven that 8 times was actually all you needed. So if 8 times was sufficient, then why did we do 16? I don't know. Do we want to waste power? Because obviously 16 rounds is going to take twice as long as 8 rounds. For the most part. Not exactly. So you're wasting time there. All right. Actually, hold on. Go back one. Okay. All right. Okay, the key length. It said Lucifer was originally a 128-bit key. Daz is a 56-bit key. But it says that 10 keys per second would take 228 million years. And 1 key per nanosecond would take a long time. Then with a parallel attack, they've proven that you could break it, and they actually did it. They won. A $50,000 machine was able to do it in 20 hours. So is $50,000 a lot of money, or $50 million a lot of money? For some people, yes. For some people, no. And if you wanted the answer, is $50 million too much? Not necessarily. So you could actually do it for $200,000 per solution. I could see some people paying for $200,000 for a key for something. This is years ago. It's quicker now. Okay, in 1997, they did a parallel attack. They took 3,500 machines. They broke it in how long? It took 120 days. 3,500 machines required 12 days to break it. Okay. 98, we had a $130,000 machine, broke it in 112 hours. Okay. Then in January 99, they broke it in 22 hours. So we're down from 112 hours to 22 hours and 15 minutes. Okay. So you're getting to the point where it's almost solvable easily. Okay, so they will not recertify it. Okay, There's some things that are on the test, for sure, positively. Complements. Okay, basically it's like the opposite of C is equal to des with the opposite of P with the opposite of the K. So what they're saying, the key complement is an issue. Okay, weak keys. You need to know complements. You need to know weak keys, not what they are, but just complements is an issue and weak keys is an issue. Okay, certain keys with half of them are all zeros or half of them all ones are bad. So does that mean as long as you don't pick keys with all zeros or all ones on one side, we're good? Yeah, but can you guarantee those keys are never going to be used? It's like y'all heard on the news about a year ago, the president of Syria got his password broken. His password was 12345. It literally was the president of the country's password was 12345. So if the president of the country does that, you don't think some idiot's not going to use a key with half zeros? It's easier to type in. So someone's going to. Semi-weak keys, okay? Just know semi-weak keys that are not quite as good. And here's some example of the weak keys. So you could have zeros on both sides, or ones on both sides, or zeros on ones on the others. So it's just keys that aren't very good. In your right mind, you would not choose these keys. But someone probably would. And if there's a flaw in it based on the key alone, that means there's a flaw in your algorithm. Okay? Okay? There's also some key pairs that are bad, and you don't need to know what they are. I'm not going to sit there and have you list these or anything. Okay? All right, there's also design weaknesses. This expansion permutation repeats the first and 4-bit every 4-bit series. When you do the assignment, you notice there's a pattern to it. So you'll notice that. And you'll be like, why is this repeat? It's because the way they did it. I don't know. Okay? The S-box derives the last 3 outputs the same way as the first. Okay? So if you came up with 2 specially chosen inputs, they would give you the same output, which is a collision, which we've learned is not bad, or not good, I'm sorry. It's like DES, we know a specific, not DES, MD5. Remember we talked about this specific bit being changed, it could produce the same output. The same problem here. Same problem there. Okay. Key clustering, 2 or more keys produce the same encryption. So if I'm encrypting something and we have 2 different keys and get the same result, is that good? No, that's not good. That's really bad. Okay. So key clusters are bad. Okay. All right, differential cryptanalysis is a powerful code breaking technique. Okay. Excuse me, uses specific pairs of plain text and keys to produce specific results, and they're able to determine basically what produces a certain output. And if you can figure out how to modify the input enough to get certain output, that's what they're talking about. It becomes a problem. You want it all random. You want it totally random. And they will not recertify DES. Okay? All right. Double encryption. So we know DES is weak. We know we're not going to encrypt it anymore, and it's only 56-bit, even though, 64-bit blocks with a 56-bit key. 56 is big, but they still consider it weak. Okay. So what if we used 2 56-bit keys back to back? Would that help? Well, so if we take a message encrypted with a key, and took that result encrypted with a key, what do you think? Would that help? But if we have 56 bits, that's 256 possibilities. So if we took 2 of those, so if we took 2 56 bits, is that equal to 2 to the 112? Actually, it's not. It's actually only equal to 2 to the 57th. Because remember, 2 to the 56th to 2 to the 57th is actually double. It's not, that's why I said 1024 to 2048 isn't just double, it's actually exponentially higher. Okay? So you can't take 2 to the 56 twice and expect it to beat 112. It's not. It's only 2 to the 57th. So if you did it 3 times, say you took it and encrypted it 3 times, it's still only 2 to the 58th. Okay? Well, the point is, it's not that great. All right, that's the end of this. I'm going to record your assignment.